So here's that number again, and I sort of put it up here tongue-in-cheek. This is the number that you mostly hear, the built environment's contribution to anthropogenic human global emissions, right? More or less 40%. Depends on how you measure it. So this, like every other number that we can show you today, is plus or minus. We don't have a lot of precision yet in this field that Larry and I are presenting about embodied carbon, but we do have accuracy. The proportions are becoming very clear, and we can see where our targets are. Buildings, big chunk of the problem, and can be a big chunk of the solution. I want to start right off by sort of challenging this notion, because perhaps in BayREN and LEED and USGBC and all sorts of organizations I've been around for 25 years, it's always been about energy efficiency. We're very focused on energy efficiency, and their presumption has been that that's equivalent to climate effectiveness. And it's not. It just isn't. A lot of overlap, and most of the time it's the same thing, and so keep doing energy efficiency, keep working on those retrofits and all of that. But there's times when they're not the same thing. Larry's firm did a study, and they found that putting that extra inch of foam insulation around the outside turned out to be the biggest climate villain in the project, even more than the concrete. So sometimes we do extra things to make a particular building efficient that aren't the best thing for the climate. Efficiency by itself is no virtue. It's just like technology. It can be used for good or bad. This is a picture of a bomb factory that the Islamic State turned a factory in Mosul from an agricultural equipment factory into a bomb factory, famously efficiently, and they were quickly grinding out bombs. So efficiency isn't by itself a good thing. And by contrast, we look at nature, and you ever been around a fruit tree at the height of its fruiting, and you see all this stuff on the ground? Well, that's not very efficient, is it? And yet somehow nature has managed to get by for several billion years, and here we all are. Everything about nature is kind of messy and inefficient, but it's very effective. So that's what we're really looking for. Put differently, why do you want efficient buildings? I don't mean to be flippant in asking that, but it's worth looking at your fundamental purpose. Why do we want efficient? Who cares? What does it matter? I'm going to guess that for most of the people in this room, and the operator of this building, and most people who live in and run buildings, the energy bill is not a big deal. What you pay to stay warm in the winter and cool in the summer is a relatively small part of your monthly budget. The exception being people who aren't as fortunate as are you and I, who don't have a whole lot of money. And there are lots of cases like this one. We've driven around places all over the Bay Area. People don't have a lot of money, or your brother hurt his back and he's out of luck now, and his whole family had to move in with you, and now there's 7 of you in an apartment, and there's the grandma who has arthritis and you got to keep her warm, and there's a new baby and all sorts of things. You have to keep the heat on. You have to keep the AC on. And there's all sorts of poor people in crummy rental housing around the state, around the world, who pay 25% of their income to keep grandma comfortable. Those really are the ones we're working towards with energy efficiency. My energy bill is fine. This is coastal California, for gosh sakes. It just doesn't get that hot or cold. But we're also interested in the Bay Area as a whole. This is what BayREN is about, is that as a whole, we don't use that much energy, that we become more and more independent of the grid, you might say. But we get to cheat a lot, right? Because we don't drill for natural gas right here in the Bay Area. We import most of our heavy industrial stuff and so on. So the accounting can be a little funny when we look at that. But we do want to be effective because it's going to affect us. I happen to choose the 2 densest areas here. This is a map, of course, of areas that will flood when sea level rises a foot or 2, which seems to be on its way. It's going to affect us a lot. And we all know, we've all studied the scenarios of what happens when the water comes up. A few communities get flooded, but all those people have to find someplace else to live, just like what's happening with the fires. So we're much more interested in climate effectiveness than energy efficiency. They're almost the same thing, but they're not. And it's really good to get clear about that, because the whole green building community is only starting to recognize that and act accordingly. So we want to do both. We want to reduce operational energy and embodied emissions, like Larry just talked about. It's not that hard to do, actually. But we also won't even get to build positive. There are built positive buildings now that have absorbed more carbon than they use. But so far, it's just a goal. It's a reach that we're looking towards. How do you know where the emissions are? Lifecycle analysis, LCA. It's a specialty field now. It's something that architects should be roughly familiar with, all of us should be roughly familiar with, but you basically have to, you spend a lot of time learning how to do it or hire people who know how to do it, and it's still an evolving field, different competing systems, competing data sets. It's a fuzzy and wild west sort of situation. Nonetheless, we do have some accuracy, even if not precision, when we study buildings or materials or products to see what's the supply chain, how much went into the air as a result of having that yard of concrete or piece of carpeting or whatever you want to know about. As Larry said, with buildings generally, most of the carbon's in structure, foundations, the superstructure, and the skin. It's generally most of where the action is, and that applies to single-family houses or multifamily houses, to most buildings. And of course, there's exceptions, and of course it varies, but that's your general picture, so that's where we're focused. Or to put that differently, it's in structural materials, mainly concrete and steel. Concrete's the big one. It's artificial rock. That's all it is. Sand and gravel and glue. And then you pour them or spray them or pack them into place to get that column right there or the floor underneath your feet or the sidewalk that you walk out onto today. And for the last 200 years since it was invented in England, we use Portland cement, which is highly baked limestone, which accounts for 8% of global emissions. Well, wouldn't it be? It's a great building product. It's a fantastic building product. That's why it took over the world. It's the most, by volume and dollar cost, it's the most common building material in the world. People love it. You can do anything with it. It just comes at this cost. So how do we reduce the footprint of concrete? Well, you can use different glue. There's people coming up with different cements, different way to glue the sand and gravel together. There's a very simple notion. Teach your engineer not to be moonstruck. Engineers specify concrete to have a certain strength at 28 days because 100 years ago, somebody figured out that concrete generally gets most of its strength in a month. And so that became this sort of sacrosanct number, FC prime at 28 days, and every engineer just does that by rote. When in fact, most concrete doesn't have to come to strength for a long time. That column was poured, and it didn't know the weight that it was designed for till at least a year later. Most concrete that gets poured has all the time in the world to come to strength. So if you just relax that requirement, you can save tons and tons of emissions just that way. You can feed it carbon, meaning you can make aggregate sand and gravel out of emissions from the power plant or the cement plant, artificial limestone aggregate. There's a company here in the Bay Area doing it, another one in England doing it. They're using some at the San Francisco airport. You can also inject liquid or gaseous carbon into the mix as you're doing it. The Canadian company Carbon Cure doing this, and other versions of the same thing where you inject carbon dioxide into the wet concrete, it absorbs it, gets better concrete, stronger concrete, and it absorbs carbon. And you can squeeze it. That's how the Romans made the Pantheon. That's how Romans made their concrete, in part, is because they compressed it. They made it very dry and compressed it. What nowadays we call roller compacted concrete, or in another terminology, rammed earth. And David Easton up in Napa, who pioneered rammed earth construction in California decades ago, and has done so much for that, wanted to make it more affordable and scalable, and he's making concrete blocks with almost no cement, radically less carbon footprint than your ordinary CMU concrete block, using earth, pressure, and vibration. There's all sorts of ways that you can reduce concrete's carbon footprint. I'm just going to mention now, because my colleague Alice will be talking to you later about this in more detail, but we're starting to write a building code in Marin County in cahoots with Stop Waste and Alameda County and others that we hope we can spread around the world, actually, to constrain the amount of embodied carbon in a concrete mix. To my knowledge, nobody's done that yet. All the green building standards say it'd be nice if you did this, and you can get a brownie point if you do so, but nowhere in the world is it law. And so we're going to try to make it the law. You have to keep it down to a certain amount. It's doable. It's not going to add costs. That's what we're working on now. And of course, the notion being, in Marin County, we hardly pour any concrete. I could fit in my coffee cup how much concrete we pour in Marin County. The idea, as I think you're all acutely aware, is what we do in the Bay Area spreads to California, what we do in California spreads to the country, and what we do in the country spreads to the world. We hope to start something here. Steel is another big one. Steel emissions are 7% of global emissions, and of that 7, half roughly goes into buildings. The other half goes into cars and refrigerators and Burning Man sculpture. And with steel, there aren't that many alternatives. We can now build with wood. You've heard of cross-laminated timber, perhaps, or mass timber structures. We can build high, large, all sorts of things with wood. Fabulous buildings, and also cheaper buildings using wood. The key is FSC stands for Forest Stewardship Council. Thank you. It's an organization for certifying sustainably harvested lumber. That's a whole conversation in itself, but we can do things with wood that we used to do with steel, and it's a good idea. Here's the big one. How many of you read Drawdown or know about Drawdown, Paul Hawkins' book? I don't see every hand going up. Shame on you. Get Drawdown. It's really cool. It's a well-researched look at what's the low-hanging fruit. What are the things we can do now to reverse climate disruption? It's full of surprises, and here's a plot ruiner. The number one thing, not solar panels, not organic agriculture, not all the things you might think it is. It's refrigerants. It's the chemicals that we use for our HVAC, for our air conditioning systems and our refrigerators and our freezers. Are these chemicals that are really nasty when they get out, and they eventually do get out. They have thousands of times the global warming potential of carbon dioxide. And so they turn out to be a huge, huge climate button. So if that's the case, then obviously we should insulate all that much more so we don't have to buy as big an air conditioner. But that gets a little complicated because insulate with what? It turns out that our favorite insulation as we try to get to net zero, get efficient buildings, is foam, plastic foam of various sorts. And it turns out that that's made with the same kind of chemicals that we make refrigerators with, hydrofluorocarbons. Same thing. And it's a dilemma because those plastic foams, like in this picture, you can do stuff with them that you can't do with anything. They're air sealed. They completely fill a stud cavity in a house. You can renovate old buildings with them. They're just you gotta love them, except that you gotta hate them because they have a bad effect on the climate. Put differently, you can look at the carbon impacts of different insulations. This is a colleague in Canada that came up with these numbers. You can have carbon emitting insulation or carbon absorbing insulation. That's up to you. But both are available now. This is a repeat of what Larry did, but it gives you some American numbers in case you were cross-eyed about kilograms per square meter. These are numbers, and again, these are very plus or minus from our, you can go to the Carbon Leadership Forum website and there's a little online calculator and you can check what your own building ought to be or what range some particular kind of building should be. But you get numbers like this and these whisper bar graphs like this to give you a sense, which we're getting a sense now of what we have been building and then what we could be building. So when you're looking for what to do as a building designer, this is a good place to start. Architecture 2330, doing so much great work with climate and buildings, has come out with the materials palette, materialspalette.org, and you can check out all the different materials and their alternatives there. So with concrete, there's all sorts of ways to lower its footprint. Conceivably, you can make it carbon sequestering concrete. With steel, you can replace it with wood, with refrigerants, insulate, and ideally not with the plastic foams, if you can manage it. Larry sort of talked about this. The folks at Architecture 2030 did the numbers and said, what we're building right now in the world is the equivalent of another New York City, all 5 boroughs, every 35 days. And that might seem like quite a lot because you don't see it. I don't see it. It's not happening here. It's happening in China and India and Brazil. And they're not building nice buildings. I took this picture driving through Beijing 6 years ago, and every window in this building is a concrete building. I doubt if it's insulated. It has no central air or heating. If you want air or heating, buy one of those little boxes like I just showed you, hang it off the window, and there's your air conditioner. They're about as inefficient in every sense of the word as they could possibly be. And this is what we're building, massively, all the time right now. So if we can start something good here and get it all the way across the ocean, that would make a difference. And we're urban. I've been hanging out with the so-called natural building world, straw bale building, and a whole bunch of really fun people who, a lot of whom are deluded to think that the answer is for everybody to build a nice little straw bale hut in the woods with a thatched roof and a couple solar panels and be off grid and everybody will be happy. That solved the problem. Except that doesn't really make a whole lot of sense. People are moving to cities. It doesn't really work for more than 0.5% of the world's population. It can't work. It's a bad idea because you end up driving up and down a dirt road, etc. We're living in cities. We're moving to cities more and more and more. But that's a good thing. Cities can be really cool, ecologically and otherwise. They're better for women. They're better for children. They're better by just about every metric. They can obviously be horrible, but this is a picture I took on a street in London. It illustrates everything nice. There are no vehicles on this particular block. There's people. The historic cities, part of why they're so nice is because they could only build as high as natural materials would let them go. And you had to be able to get up there, up and down with stairs, no elevators. So they weren't tall, and they had admitted light and air to the street. And in every sense, they could make a really nice landscape. One of our naturally occurring responses to that is the so-called podium building. We're seeing lots and lots of these in the Bay Area and elsewhere for infill projects to get more housing, 5 wood frame stories on top of a concrete deck and parking underneath. It's a very effective, logical step. This one is David Baker Architects, and I think it's in Berkeley. And it illustrates how we could be doing urban building with much more effective. I know that it's going to be a close to net zero building because it's David Baker Architects. That's what they do. But from the embodied point of view, you could have a wood structure rather than steel, or if you're framing it with wood, get FSC certified lumber. You can use carbon-based insulation rather than plastic foam. And you can use low-carbon concrete for the podium structure. And there's all sorts of other things you can do. This, of course, is just a quick run-through. But I think you get the idea. A lot of the technologies that are evolving for embodied carbon, for low-carbon construction and even carbon sequestering construction, they would go zooming forward if we just incented people. But there's no money in it right now. Till we put a price on carbon, all this stuff is basically constrained. It's hard to compete in the marketplace. Carbon payback is just to reiterate what Larry alluded to before. You might have wondered what he meant when he said, what's the payback on some solar panels or a layer of insulation or something. It simply means if there's so much embodied carbon in it and it's going to save a certain amount per year, in how many years has it paid for itself from a carbon accounting point of view? This is a field we're only starting to articulate the question and think about, much less be able to answer it. When is it worthwhile? If a PV system on top of a building won't pay back for 15 years, is that worth it? Probably, but we don't even know how to evaluate that one yet. Some things are obvious, no, don't do it. Some things are obvious, yes, do it. And there's a lot of things in between. So it's just part of the emerging scene. We're laying track as we ride the train here. And I think, well, I'm done. So this is a book that was referenced. Larry contributed to it, all sorts of our colleagues working in embodied carbon. And I hope you'll find it useful. It unpacks all of this stuff in a great deal more detail.